We will kick off the last segment with three sort of highlight talks, 20-minute talks, as I said, from researchers who we are very happy that they came here to CIIRC after significant experience abroad. And so we will see some of their latest research results, and at the end we will have a wrap-up panel discussions about the trends in AI. So don't stay with us if you want to learn about well, at least some of us are thinking about what's going to be, what is interesting, what's the trend in AI, what may be the new breakthrough. Stay for the wrap-up panel at the end. And so let's start. This segment with welcoming Torsten Sattler on the stage. Torsten, thank you very much for being with us here today. So Torsten is a senior researcher in this building in our institute, where he's heading the Spatial Intelligence Group. He's known for his influential work at the intersection of 3D computer vision and machine learning, with especially sort of localization, which I'm sure you will see some of the results. Just to say a little bit about Torsten. So before he joined CIIRC in July 2020, he was an associate professor at the Department of Electrical Engineering at Chalmers University at Sweden. Before that, he was at ETH Zurich, where he first started as a postdoc, but then he was for several years a senior researcher. There he got his PhD from RWTH Aachen, which was already mentioned here several times, a great university in Germany. So, Torsten, it's really wonderful to have you here, and please, the stage is yours. I'm very happy to hear your results.
Thank you very much for the nice introduction. I'm going to talk about 3D reconstruction, visual localization, which are two of the main research topics of the group that I'm building here at CIIRC. Let's start with the visual localization problem. It's rather easy. We're given an image, and we're tasked with computing the exact position and orientation from which was taken in a given scene. Why are we interested in this? There are multiple applications that build on top of this. One is augmented reality. This is some work that we did a few years ago, nearly a decade ago actually, where we want to display virtual objects into the field of view of the user in a way that they feel like they are part of the real world. So this is what we did back then. Nowadays, if you have a Google smartphone, you can actually get something similar as part of Google Maps, where you can localize yourself by sending an image to a server, and then Google will give you walking instructions based on where you are. Another interesting applications are robotics. So this is a project that I was involved on while I was at ETH, where we wanted to build a gardening robot that can trim hedges and cut roses. And for this task, you need to know where you are in the garden in order to figure out how to get to the topiary that you want to trim. Last application, this is a recent work. This is joint work with Gerard Ponsmall's group at the University of Tübingen, where we mounted a camera and multiple IMUs on humans, and then this allows us to track the motion of the human, and by extension, actually figure out how they interact with the scene as well. Good. Let's talk a bit about what localization, how this is done technically. The typical approach is you have some 3D model of the scene. And for a new image, you try to establish correspondences between pixels in this new image and 3D points in the model, which you in turn can use to figure out what's the exact position and orientation from which the image was taken. And this is still, I worked on this type of methods during my PhD, and this is still state-of-the-art to some degree. But it typically requires a specialized scene representation that's just built for the purpose of localizing images. And if you think of like localization content of applications, this can be a disadvantage. If you're thinking of a robot that needs to navigate somewhere, needs to have a scene representation that's suitable for navigation, then having to build and maintain and synchronize multiple maps is effort that you probably don't want to do. So one of the things that I'm interested in terms of research is figuring out what are good, appropriate scene representations for visual localization that can be also used for other tasks. One thing that we recently published is work by one of my students, Wojciech, where we were looking into using 3D mesh models that are dense and can thus be used for, say, occlusion handling in AR, path planning in robotics. And we wanted to investigate how we can use them for localization. And what we actually noticed, what I thought was interesting, is that like these localization pipelines that I've shown cannot only establish correspondences between like photorealistic models, but you can also establish correspondences between a real image and such a rendering. And not only like such a rendering that's close to photorealistic, you can actually have correspondences with rather abstract styles. So here you just render like a shaded version of the geometry without any textual details, which I was very surprised by when I first saw the result, which I think is interesting because it opens up new avenues of research. One thing is, this is work also by Wojciech, which we'll present at CVPR this year in a few months, or next month actually, where the goal is, rather than like building an accurate model, can we download models from the internet that other people have built? And those don't necessarily need to be like highly accurately. Here you see the range of things that you can see. This is Notre Dame. Some people just upload like a set of planes that, as a human, are still like, this is Notre Dame, if I tell you. But our question was, can machine learning algorithms or like localization algorithms handle this? And to this end, we're going to present like a benchmark study that uses different, like real images and tries to localize them against like different models of different quality downloaded from the internet, with one of the motivations being that if you're interested in or tasked with, for example, designing an AR application around St. Vitus Cathedral, then this technique would, or this set of technologies would allow you to just download models from the internet without having to do data acquisition and 3D reconstruction yourself. Anyways, if this is interesting to some people in the audience, the benchmark dataset will be online soon. So this was work on trying to improve the accuracy and robustness of localization algorithms. Another important question is that's starting to get more traction in the research community is, what about privacy? So in practice, what you would build like a system, something that starts with edge device such as, say, a HoloLens or a mobile phone that take images that get transmitted to a server where localization happens, and then the server transmits the position and orientation back. And turns out, like, obviously this is ripe with potential privacy threats. So like a malicious server might learn details about, say, how certain parts of the environment look like by analyzing the images. So there's work on this topic that tries to send a more abstract version of the images to the server. Storing user-generated content on a server owned by a large company is a potential privacy leak, because it might contain information that you don't want to share with someone who gains unlawfully access to that server. And there's some work, again, on designing representations where you lose certain privacy details. What we're going to show, and this is work by one of my student Kunal Shilani, is that also the last step where you do localization and transmit something back to a client is a potential privacy leak. Because just by querying the server, an attacker can learn content about what's in the scene. And it turns out that this is actually, like, the reason why this attack works is that we're starting to build localization systems that are robust to strong condition changes. So ideally, we would like localization to work under day and night changes, in the context of robotics. The robot should be able to operate 24 hours a day, not only at like around noon. We want systems to be robust against motion blur, which happens frequently, and we want to be able to be robust against viewpoint changes. And this desired robustness to changes in shape and appearance actually enables like potential privacy-based attacks. And our attack is rather simple. We assume that the attacker has some video sequence of some object. So for example, you could have downloaded thousands of pictures or video from the internet. The attacker builds a 3D model from these images so that they know where in space these images were taken, and then queries the server with each of these images, gets a pose and return back, and then having the poses returned by the server, and from 3D reconstruction aims to place this object in the scene if possible. And if you have enough images and do this enough times, you can start recovering what's actually in the scene. So you get an idea of the scene layout. So here's the qualitative result. On the left, you see the actual scene with the objects that we try to recover highlighted. And here you see the results that we got by querying with similar but not fully identical objects. So you get a very good idea of what is in the scene, what's the placement of the objects, which to some users might already cross the threshold of this is private to me or not. So here, the takeaway is that what we actually desire in localization algorithms in terms of robustness could also backfire in terms of privacy. I think there's a lot of interesting work to be done there. So much about localization. One thing that we noticed, and I showed this slide before, is that we get better results if we try to build photorealistic 3D models of the scene. So, how do we do this? How do we get photorealistic scenes? That's the second main research direction of my group. And I'm going to show a couple of results. Here you see results of an existing approach in rather complex scenes. It's a machine learning-based method. What makes these scenes complex is not the structure of the scene, but that there are relatively few images observing them. So each part of the scene is only observed by a few images. So you get very few constraints that you can use to reconstruct the scene. And as a result, you get these jumbled things such as like geometry floating around, like very unclear structures, and so on and so on. And the work that we presented last year at NeurIPS, and this is work with Andreas Geiger's group at the University of Tübingen, uses a very simple scheme based on the observation that neural networks nowadays are quite good at predicting distance of structures to the camera and normal. So you can take an image, you can run it through a network, and you get a depth map which says this pixel is roughly this far away, and you get a normal map that says the corresponding surface element has this normal. And while this is not super accurate, you can use it as priors for the 3D reconstruction process. And using these priors can have significant, result in significant differences. So here you see the original method, and here our adaptation just by integrating the priors. You see that we can recover the shape of the skull very accurately. We can get a much better picture of a reconstruction of the room, both in small scale and at large scale. And it doesn't add much computational complexity on top of this. If you're interested in trying this out, we recently published a software framework called SDF Studio that implements this technique and other 3D reconstruction, state-of-the-art 3D reconstruction technique. It's available on GitHub if you want to try out. So this work was mostly concerned about the quality of the surfaces. The last thing that I want to show is ongoing work with one of my students, Jonas Kulhanek, on trying to build like scene representations from which you can render photorealistic views. And so these are renderings of the scene representations. These are not images. I just want to mention this because they are very close to each other. So this is the type of quality that you can get with a technique based on something called neural radiance fields that I'm not going to go into detail. If you want to be convinced that this is not a real rendering, then look at the depth maps that we get from the reconstruction process. Here, like colder colors mean closer to the camera, warmer colors mean farther away. And while we're able to actually reconstruct most of the scene quite well, there are some artifacts here on the table that show you this is actually not a real image, but this is something computed. And with this, I would like to actually wrap up. So in general, what my group works on is building, like reconstructing the world in a manner that's photorealistic, but it can also be used for visual localization, including the question of what's actually, how do we need to build scene representations that might not be photorealistic, but that ensure certain levels of privacy. Thank you very much.
Thank you very much. Thank you very much, Torsten. Lots of wonderful results. Any questions from the audience? If maybe, yeah, here's one.
Yes.
Like in the last movie, how computationally expensive is it to generate that?
So the results that I showed are, I think, after 24 hours, but you get already get quite good results after 40 minutes. That's on an A100 GPU, multiple ones, I think. That being said, the implementation is not particularly efficient. I would expect that you can get like comparable results if you really tune it in 20-ish minutes. And we are looking into actually making this much faster by introducing approximations that will reduce quality but will make training hopefully significantly faster. Yeah.
Any more questions from the audience? There were some people from industry also. How far, just practical question, how far we are from just having a mobile phone in our hand and scanning an object like this to be, I mean, for robotics, we always get these questions like, you know, to manipulate objects, can we scan them quickly? What's your take on this?
So I know that there are startups that actually do this on the phone, not using deep learning-based techniques, but like classical multiple view geometry stuff. Nowadays, you can also see more and more applications that actually take images and then send them to a server and do the computations there. This type of object should still be fairly simple. It has enough texture. There are like harder things. It's actually one of the things that we would have shown in the testbed tour. One of my students is working on reconstructing objects so that they can be used for pose estimation and object manipulation tasks for robotics.
So do you think actually it's usable already in some cases now? Or is
I think in some cases, yes. It depends on the quality of the object and how much time you're willing to spend there. But I think like real-time 3D reconstruction is certainly possible. The quality that you get out of this is then the question.
Okay. So that's what, one of the things you can improve potentially.
Indeed, yes.
Any more questions from the audience? If not, let's thank Torsten very much.
Thank you very much.